Okay, hello dear Meatbags. We are starting our first lecture on hyperbolic geometry in art, physics and data science. And okay.
You have to remind me to enable recording.
I actually don't understand what did you say. Maybe you can write it in chat and one day I will read. Maybe in break. Okay. So my name is Yaroslav, and I'm going to teach you something about hyperbolic geometry. Actually, there is a whole plan. So our course is motivated by some applications from recent time. It is also motivated by complexity of the topic. Actually, lots of people fear of hyperbolic geometry, and also it is motivated by difficulties even for mathematics students to understand multi-dimensional geometry. It is actually motivated by exceed of raw material on topic in the web. I collected a lot, and I watched it for this course a lot more. And actually, this is very beautiful topic. So, I was told that students are motivated by applications. So let us talk about what do we need some geometry, why do we need to study geometry. So actually, for example, I will not duplicate slides in my speech, but okay, let me tell you that, for example, usually when data scientists are evaluating the models, they should sometimes work by their hands, by visualizing, by some how to say this, by drawing some pictures. And so we need to express our information, and so Euclidean geometry, standard Euclidean geometry that is taught in schools is good for this, but it is not enough. So this is not enough for some language models, for example. Actually, throughout this course, you are encouraged to add your comments, ask questions. Actually, there will be lots of exercises, and we will make some stops for your questions. So don't hold yourself. Yeah. So our course is organized in the following way. So I chose different languages of expressing mathematical things. There is an algebraical way, geometrical way, combinatorial way, abstract way, an experimental way. Maybe you know some other ways. And we will talk about all these ways to think in hyperbolic geometry and multidimensional geometry. Okay, so let me open the first slide. Okay, some historical introduction. Geometry started in ancient times when people needed some language, and some methods, some models for different tasks like architecture or, I don't know, material storage, some other things. It's at one day, ancient Egyptian mathematician Euclid introduced us his axioms for geometry, and this was about some straight lines, some measurements, some geometric constructions with this ruler and circle, and also he introduced some foundations of mathematical logic. So, why axioms are important? Actually, they were invented from reasoning. You need to reason sometimes. Here you will see some optical illusions. Here are two illusions with straight lines. Horizontal lines are straight, actually. Probably, I don't know. You might be agree from the first sight. Some children, whom I talked about this, said directly said in one moment that this is just obvious for them that they are straight. So there are actually some illusions about half planes, some illusions about equal segments. So you need to prove that these segments are equal somehow in practice. So here you see lots of squares. They are squares, I swear. And yeah, this is some illusion for equality of areas. So this is a proof, some proof that 64 equals 65. You might find some mistake here. Let it be the first exercise, actually. No. What? What? Repeat.
I mean, green and red either have a difference angle. But I could use full screen.
I see. Okay. How to do this, actually? Okay. Mm-hmm.
If we calculate angle of green
Mm-hmm.
and straight line red, so we allow the difference angle.
Actually, no. For now, no. There is some different explanation. Angles are different in the right side, but not in the left picture. Since right, but there is no red in the right side.
So you right in what you say and right in what he says.
So you are talking about right red triangle, yes? Yes, there are. Okay. The angles are different. Yeah. And actually, on the right picture, the right of the right, there is no triangles here, actually. So yellows are not triangles, they are quadrangles. Okay. So some illusions about triangles. You probably can see some triangles, but there is just one. Yeah.
Are these optical illusions somehow connected to the terminal?
Yeah. We will use some ideas from it actually. And so there is an illusion about the violation of geometric inequality, triangle inequality. So parallel lines, another parallel lines. Okay, yeah, circles. Circles we will need actually. We will need a lot of circles. And some circles with diameters, and this we will also need. So another diameters. For now I don't see any motion, but I saw. Okay. When I was preparing the slides. Okay. So what is the Euclidean fifth postulate? It is about some parallel lines, the existence of parallel lines passing through some points, and here you see some formulations. So actually what it is. There were some axioms about more or less obvious axioms that can be checked by experiments, and the parallel axiom is not so easy to check, since you cannot check directly if two lines are parallel or will intersect at some very distant point. And this was the challenge for a mathematician for 2000 years, and they tried to derive this axiom from others. So you see some pictures. The first picture, there is just one parallel line passing through white point. The second picture, there cannot be any parallel lines. In the third picture, there are at least two parallel lines, and between them there should be infinitely many. Okay. So some historical introduction continues. So people tried to derive it with lots of ways, and they failed because actually they assumed some equal statements. So let me say to you that actually what we will not meet in hyperbolic geometry. We won't meet any triangle with sum of angles equals to 180 degrees. We won't usually meet two triangles. However, but no, we will meet lots of triangles with equal angles, but they will be always equal. So Pythagoras theorem is equivalent to this postulate, and lots of other things. So I just copied several of them. So no similarity of triangles, and no rectangles, no what is interesting here, no upper limit for the area of a triangle. So time passed after Euclid, and in 19th century there were even in 17th century there were several people trying to prove this fifth postulate from the contrary, and these three guys just invented a whole theory for just the proof from contradictory, and Yeah. So in Russia, we call this geometry as Lobachevskian geometry, since actually it was more or less the most stable publications, so to say, from him, because Gauss didn't publish anything. This was found just in his diaries. Bolyai stopped his work when Gauss wrote him, and he feared from Gauss, as I was taught. And yeah, so this is some scientific competition. Okay. This was called hyperbolic geometry. Somewhat later, they didn't see anything. These three guys didn't see any visual model. They worked from abstract scenes. So let me formulate the axiom for a given point, and not on the line, not on the given line. There are infinitely many lines passing through the points that are parallel to the given line. What is parallel actually? Parallel means that this is not intersecting. This is just plain axiom. We will work with in many dimensions, but since many dimensions is reducible to just 2 dimensions, we will start from here. So, what is the first observation from this geometry? Is for a point not in the line, there is a spread angle. Spread angle for parallel lines passing through this point, and so you just draw parallel lines that are no, all parallel lines that passing through A, and there will be 2 lines that are limiting for others. They will be all others will be in the angles between them, and so this is the spread angle. Yes, and this, yes, we will get an intersecting line for any angle less than this, but actually this angle depends on the point A. This angle depends on the distance from the point to the line. Yeah. So I forgot to erase some lines. Okay. So there are some standard other axioms, some usual stuff, like through every 2 points there is passing exactly in one line. Plane is divided by a line into half planes, and some others. You can measure your segments, your distances. You can measure your angles. You can introduce area. Lots of things. There are lots of similar theorems to Euclidean geometry. There are theorems for equality of triangles, angle, side angle, side angle, side, side, usual stuff. You still can draw perpendiculars and lots of other things. So this is just usual stuff. Some pictures will start soon. Don't worry. So there's also some different theorems like equality from 3 angles. So if triangles are similar, they are equal. So parallels, Pythagoras theorem is not working here, but there is an analog. We will talk about this on the third lesson, actually, when we will talk about some formulas. So today we will see some. We will work with some visual introduction, but don't worry, you can think about something even today. So this was a slide about this was this slide is intended to show you that some idea why there is aperture limit for a triangle area. Actually, I forgot to add the word area. Okay, there is some iterative construction for triangle ABC, repeating it as triangle DCB, then constructing parallel lines B1, C1, then repeating the same contraction for A, B1, C1, and so on, and your triangle expands and expands, and actually there is a way to show that there is no place for as parallel line. So I do not want to stop here. And what? B1, C1? Well, for example, you can, okay, let me show you some idea. Actually, if you draw, for example, if you draw a line BD for the angle, so yes, here's the mouse, with an angle DBC equals to ACB, then these lines will be parallel, actually. AC and BD. Yeah, so you can actually do the same construction for CBD and BD-B1, and then these lines will be parallel, and so on. Okay. So this was just some idea. Never mind, we will go to the modules shortly, in a short time, so abstract things will end soon. So what? There is an ideal triangle consisting of three limiting parallel lines. This is actually a triangle, if you may say so, because there is no angle in it, just three sides of three lines, and they're forming angles of 0 degrees. So and this is a triangle of the most area. And actually, why do I say so? Actually, there is the first theorem I want to present. This is a theorem for area formula of a triangle. So let me denote F as F on phi as an area of such a domain. Then you will have such an equation for function f. What? T is an area of ideal triangle. So here you form ideal triangle, here you also form ideal triangle, and so that's why these formulas work. So you have such a chain of consequences, and you derive that f on phi is just linear function on phi. And so area is just depending on angle phi linearly. And for triangles, there is a formula that its area can be computed like this fraction. Okay. So if you want for me to explain more thoroughly, you may ask, but actually, if you want, presentation will be available for you, so you can think through it later. So, okay. Actually, you may also ask me to do this in the next lesson, but might be not very interesting. I don't know. Okay. So this is what I said. So yeah. So this is the first break for questions. Is there any? Yeah.
Visualize what we have just done. I mean, I've seen some models.
Yeah, you've seen some models. Yeah.
They constantly rise in your mind and you see what you do. But this should be done axiomatically, right?
Yeah, this should be done axiomatically, but what do you mean this should be done axiomatically? Actually, there is a proof, and for that your model there is complete classification of models for this geometry. So these models depend on parameter t, for example, where t is an area of ideal triangle, and this will be actually there is a proof, and for applications it might be enough. I don't know.
First, you said that if axiom is given to the spectrum that we have enough unit for triangle area, right?
Yes. So there is this is equivalent to there is no upper limit for triangle area. Yeah.
So is it equal to Euclidean or to hyperbolic?
Well, what it is? No, this is not equal to hyperbolic actually, because, for example, there is a spherical geometry where you also have upper limit for triangle area. Euclidean you don't have, because well, you know you can construct lots of similar triangles here.
What is it equivalent to that?
Actually, I don't know. So, what do you mean equivalent? Because equivalent it should be in the context of other axioms, right? In the context of other axioms, right? So you have lots of other axioms, and from them you derive some geometry.
So we feel that that's first order, right? And the other is
What?
Yes.
Here? Yeah.
Here we have like 9.
Yeah, like 9.
Basically, it is 4 and then something. I mean, why fifth is all?
Why fifths? Because Euclides just formulated 5, and he grouped several axioms into one, and this is just so this is formulated just in distant way.
Those 5 are actually something like this.
Yeah, those 4, first 4.
Here we don't have it.
No.
And then you say that we have a statement of that there is an upper bound of the triangle area, right? And which comes besides all this.
What? I don't get it. Sorry.
Okay, so what is this thing about triangle area?
What is this thing about?
Additional to what we have
Well, you can. No, this is just a conclusion from the hyperbolic action, for example. Maybe I formulated it incorrectly. Sorry. So since no, I didn't. So sorry, I didn't formulate it that it is equal. This is not equivalent to hyperbolic action in any way. But yeah. So what?
So what is this? And where does it come from?
There is no action here. Sorry. This is just some theorem. Okay.
It's an action, right?
Well, you can postulate it in a way of action. I don't know.
Okay, I don't know.
Please ask question.
I can allow anyone to ask more. Because I have done my thing.
Okay. Maybe the proof. Okay. Which part did you not get? Okay. Sorry. We won't do this for now. Okay. You can check on it, and maybe I will do this the next time if you will be asking. Okay. Let me go to something interesting for some pictures. Okay. So there are 5 and even more models for this geometry. We will talk about just 5. So since they are the most simple one. Why this slide was empty? Okay. So the first one is the simplest to explain and the hardest to compute. This is a Klein model or Beltrami-Klein model. It was invented in 19th century. So this is just when you think of your plane as an inner part of some circle, or your space as an inner part of some ball, and lines here are just short sections of lines for your with your ball, and so you can see from the picture that through P there is lots of parallels for A. Angles and length formulas are not trivial for this model, but I will give it to you for this on the third lesson, but you can also derive it from what I will say later today. This won't be easy, but okay. So there will be lots of pictures like this. This is a tiling of this model into equal regular pentagons. What do I mean by regular pentagon? Regular polygon is when your polygon is having equal angles and equal sides. So you probably can see any how to say this, any sense how to derive such formulas, but actually you might do this as a very complicated exercise. And so this is some tiling. Okay, so another empty slide. Okay. So the second model is Poincaré model. This is less trivial to explain, but more easy to compute. Actually, so what it is? You take as the lines circles that are orthogonal to the boundary of your circle or to the boundary of your ball, of your sphere. Actually, I forgot to tell you that there is what is this ball? What is the sphere about? What is the circle? Actually, the boundary is not in the model. They are somewhat like directions for the lines. So these points on the circle is just some directions for your lines, and so actually for this model you have a property that angles here are just angles between corresponding circles. What do I mean by angle between circles? It is an angle between tangent lines for these circles. So you can visually see that if you imagine some tangent line for the boundary and for these lines, then they will be orthogonal. And yes, so there is some tiling of equal quadrangles. So actually, the first exercise is to compute. They are regular quadrangles. The first exercise is to evaluate these angles. Can you do this? You can always ask some hints if you want. Yeah, 60 degree, right. Because what? Because we have just 360 degrees around any point. Okay, good. Lots of such pictures actually. So there is a tiling of regular octagons, which are divided by equal quadrangles, not regular quadrangles, but equal. So try to get some angles here.
90.
90 where? In which? 90 in the middle, right? Not all the rest, because, for example, here you so in the centers of the red octagons, actually in the center of each octagon you have 90 degrees, and for the angles and for the boundary vertices you have just like what? 60 degrees, not always
60 and sometimes 120.
120, yeah. Okay, good. So this is just some picture for ideal triangles with some inner structure for them. Okay. Another ideal triangles with some tiling. So those ideal triangles actually are derived from each other by symmetry relation for the sides of them. So if you, for example, take this side and you symmetrical construct mirror symmetry for the black triangle, you will get this white triangle. And this is the way to construct all the triangles here. So this might be seen on the right picture. Might not be seen. Okay. Okay. Lots of parallel lines, motions. So this is not a rotation. This is some shift, actually. We will talk about this later. Any motion on a plane is given by positions of 3 points, or future position of 3 points, even for boundary ones, ideal points, so-called. And so what will become a blue triangle here? What? Maximum value. What do you mean maximum value? Yes. They will all be of equal area. Actually, this cannot be seen from this model actually directly, but yeah. So I mean, so you see some motion. So what do you mean? Maybe this is very trivial, but which triangles will become blue one time? One containing what? Zero. What is zero here? Okay. This is not a rotation around this upper point. If you mean this. Yeah. Yeah, I mean, these triangles will become blue one. These triangles will become blue one.
The triangles that contain this center.
So you see, this violet triangle is not containing this, and then it become blue one. So when will this triangle will become blue? Well, not all adjacent to the previous one. So actually, you can see some triangle below. It is not blue at any moment. What? What? Repeat, please.
Equal angles.
Equal angles? Which angles? All the angles here are zero, actually. Okay. Let us try to think about it.
So, I mean, what is going in this conjecture that the blue one contains the center of the circle?
Yeah, the blue one contains the center.
Okay, so nothing wrong.
Yeah, nothing wrong.
But it is not enough.
These triangles will become blue one.
Those that contain center of the circle.
For example, you see this violet triangle is not containing.
It is not blue.
And then it becomes blue.
Okay. So the distance to the zero becomes less and less, and at some point it reaches zero, and then it becomes blue. I'm not sure what the hell is happening.
Okay. So maybe bad exercise. Okay. Let me answer what did I mean. So you have this sequence of triangles, and they will one day eventually become blue one, since they're somewhat like rotating this way. They are not rotating; they are shifting actually. Okay. So what is here instead of cellular grid? Here you see lots of lines that are either parallel or perpendicular.
Still, what was the exercise and what was the answer? Could you elaborate on that? You said that there is a sequence of triangles that like are shifting. So what?
Okay. Okay. So you see. So you might see the sequence of triangles coming for this way. Yeah. They will all become blue one
Yes.
at one time. So this is the answer. Just this. Okay.
What was this the question?
Yes.
It was not obvious at all.
Not obvious. Okay.
You asked what to do.
Okay. Yeah, I apologize. Maybe a bad exercise. So here you see. So I said earlier, what do we see here? And actually, what is interesting here? This is an example of ternary tree. There is no cycle in this graph of points and segments. Yeah, this is a ternary tree. One vertex is a root of degree 4, and the others are ancestors of degree 3, of assessing degree 3. Yeah, branching number is 3. This actually is an idea for what? For applications in information geometry. So this is there are lots of such constructions actually in hyperbolic geometry. This is not possible in Euclidean geometry in the sense that actually here all the segments which are not containing any point, an intersection point, are equal. So this is a tree construction on the plane. Okay. So this is just containing the previous construction actually after some motion, and those are right-angled hexagons and even regular hexagons. Okay. So here is what it looks like to move your points on the plane in this geometry. So on the central one is some rotations, and left and right are some shifts. Those are called hyperbolic shifts. Those are called parabolic shifts. In the middle, the elliptic shifts. Whatever it means for you, but I will explain it later. Okay. The third model, upper half plane model, or you can consider in multi-dimensional cases half space model, with lines circles or lines orthogonal to boundary. Yeah. In this model, you also have this beautiful angular property. So angles are just angles between corresponding circles. So this is some tessellation on heptagons, even regular heptagons. Okay. Some motions of hyperbolic of a model of an upper half plane model. So there is an exercise. Can you spot the center of rotations? There is a center. Those are some rotations, and can you spot the center? What? In the top where? Here? No, they are moving. Rotation is not moving, yeah? What? Yeah, I see. So, we live in Russia, and I didn't activate my Windows. Okay. So, yeah, this point is not moving, so this is a perfect rotation center. Okay. Fourth model, hyperboloid model. So, yeah, let us watch some video. This is actually a model of which lives in some multidimensional surface. For the plane, you just put n equals to 2. For space, just n equals to 3, and for line, n equals 1. So for n equals 1, you have just the usual hyperbola x squared minus y squared equals minus 1. Yeah. So, yeah, this is a rotating version of lesser dimensional hyperboloid. You can rotate it along the vertical axis and get your beloved hyperboloid. Okay. Actually, I didn't find any video for rotating hyperboloid in the web. This is actually set. Please someone draw any video. So actually, I didn't formulate it clearly for now. The model here is when you take the upper side of this hyperboloid. Lesser is not connected in any way to it, so you just drop it out. And this model is actually the most physical one. So if you're embedded in space in differential geometric terms, so then the distances here are the length of stretched strings between 2 points. Angle is an angle between tangent lines. Areas are areas on surface. Motions are linear transformations of containing space, preserving hyperboloid. Actually, I didn't tell you. No, I see. Yeah, sorry. Wait. Okay. Actually, I didn't tell you what are the lines here. Lines here are actually some sections of planes with this hyperboloid. And in multidimensional case, subspaces are sections of this hyperboloid with linear subspaces in this n+1 dimensional space. We will, Yes, passing through the origin of coordinates. Yeah, sorry. Subspace, I mean linear subspaces, not affine subspaces, yeah. Okay. So, okay. So this is how tiling looks like on this model. I just adore lots of videos about the geometry. So I will show you lots of them. So, yeah?
So it was exactly the illustration how to connect this, for example, where transition.
Yeah, this will be. The previous one? No, there was no disk. There was no disk. Okay, yeah. There could be seen some disk. Okay. So this is a relation with Poincare disk model. So you see that the boundary is actually an infinity here. Other side of reality, or other version of reality, actually other point of view. So, yeah. Okay. And the motions in the geometry. No, not motions, but yeah, well, actually motions and ideal triangles. So now is the time for making a break for 5 minutes. You can walk around, drink some water.
Сильно быстро нельзя, потому что не практически. Всякой цели. Вот тут специально записаться.
Окей. Okay, let us continue. So this was the fourth model. And the fifth model. This model is about half sphere, hemisphere. Lines here are circles orthogonal to boundary, so they are just vertical ones here, and subspaces are spheres orthogonal to boundary. So actually, this is my favorite model because it combines some simplicity and lots of properties from other models. Since lines are just vertical sections of planes, just sections of vertical planes intersecting this sphere. Yeah. Here are angles. Here are just angles between corresponding circles. Still, no simple formula for distance between points. This is just but personally, I like to work in this model. Okay. So there is a relation of this model with the disk circles model, Poincare model, with this projection. Projection is from upper point of sphere. We will see this in some video. Okay, let's open. So this is a hemisphere model. Source of light. So if you take the source of light to infinity, then it will become just a Klein model with circle lines. Yeah. And if you place source of light on the just the border, you and project, so you just get half plane. Okay, some motions of this model. Here's how they look like. Yeah, relation with Poincare model. Okay. Yes, this is another video of this. I don't know. If you want, you might look at it. Okay, you have a link. Actually, there is a video for some concepts of Voronoi diagram in this these models. We can watch this if you would like to. So, and yeah, Voronoi diagram. Okay, let us watch for short. Okay. Huh? Why?
Visualizing the hyperbolic curve diagrams by previous individual. In hyperbolic geometry, there is this infinite linear lines passing through a given point and not intersecting another prescribed line. Several models satisfy the axioms of hyperbolic geometry have been dealt with in Euclidean geometry. We bisect the hyperbolic plane. We define a model where the new hyperbolic segment is a Euclidean segment, and the red orbital perspective is a Euclidean line curve.
So this is an orthogonal bisector.
In the point here is the model. The segment in the bisector are arcs of circles perpendicular to the limit circle. A conformal model pursues angles. That is, Euclidean angles mentioned in the model inside the hyperbolic angles. The hyperbolic bisector is perpendicular to the hyperbolic line segment. This is checked in the frontier conformal model. High models are conformal, but also the limitation. Hyperbolic geometry is an abstract geometry fulfilling the axioms of hyperbolic geometry. There exist several models of the hyperbolic plane described as Riemannian and curves embedded into equal to equal space. High models use for computing geometry structures and linear model visualization. Other models have also their own merits. Since the complex sector is defined, the hyperbolic model lines are fine.
So Voronoi diagram is just some important concept from usual geometry. You just take several points and you draw for each point you draw a region of points which the closest point in the set is just given one. So for this point, this region is this polygon. These points are closer to this point than to other ones. Yeah, this is the definition.
It is equivalent to a flipped diagram, also called a weighted corner view. The flipped diagram contains several weighted points generated in similarity. The common formal diagram can be rendered in a clear form of this model.
Yeah. Three models.
Realization preserving as boundaries and describing Megas transformations. We can for example have all translation in such a Megas transformations. Here we choose two positions in front of the step from the snap angles and go ahead along translation. And now we can get our operations. We take over the file from the diagrams. This is the first order. When we look at this composition, it shows the process angle. Since the contour of our formal diagram is three order from outline. Let's increase order.
So the points highlighted are just two nearest ones. Okay, for second order Voronoi diagram.
So what exactly the lines are there?
Lines, which lines? This?
See some line, right?
Yeah. They are orthogonal bisectors for some segments between the points from the set.
Between like pairs of points.
Yeah, between like pairs of points.
One and a pair, or like a pair and a pair.
No, just for pairs.
So we have way more like segments, right?
Yes, but the boundaries are formed of just segments from these orthogonal bisectors. Third order, fourth order, yeah. Okay.
And actually, it is funny to know such a concept as coordinate diagram and three-order coordinate diagram, but like when we use it somehow, it's just funny.
Probably for coordinate diagrams in hyperbolic geometry, I don't know for now, but in Euclidean geometry, sometimes yes.
It's connected to triangle.
What?
Triangle.
Don't understand.
Okay, never mind. Like,
Okay. So this is a video of relation between 5 models. Okay, so questions so far? No? Okay. Well, I don't know. For someone this is clear, for someone I don't know. Okay. Okay, don't suppress the others. Yeah. So if there is no question, then I continue to the third part. Okay. There is a part about art in hyperbolic geometry. So we will see some computer games, we will see some art, we will see some plays. So the first artist introduced is Netherlands artist Escher. He drew several pictures in a hyperbolic setting. So this is circle limit, another circle limit. Probably some see some angels and demons. Okay. Yeah, fish, the most famous one. Okay. So this is a modern artist. Here is his website. Another probably artist, but also actually a teacher. This is a kangaroo tiling. On the link below, you can find some code for programming pictures like this on your own. We will discuss the formulas for it later, actually. So, another artist. Okay. If you want to go, for me to go slower, ask. Okay. So this is another Escher picture. Method behind is actually copying by motions all these objects. So here you can see those angels and demons in half-plane model. I want to read from this. Please give me this. Okay, this was a joke. Okay. So, how to live in hyperbolic world? Basically, according to Einstein and his colleagues, we are already living, since hyperbolic geometry is actually a geometry of a space, but our space is so slightly curved that we do not see this from our point of view. Probably in some very strong telescopes we can see, but this is not very easy. For me, at least. So, how can we live in this geometry? Here, so there will be a lot of advertising, and this is some chess in hyperbolic geometry. Okay, so for example, bishops are working across the lines. This is, yeah. So you can see, so you can see lots of lines as the walls. Yeah. What? Okay. Yes, this game is popular actually. Yeah. So you should collect as much treasures as you can and survive somehow in this strange hyperbolic world. Okay. You can actually experiment with different models in this game, but it's sometimes tough. For example, hemisphere model is not very practical in this game, but nevertheless I love this model the most. Okay, Rubik's Cube. Here are some rotations. You can see consecutive rotations. I just screenshot to you. Okay. So here will be some videos. So this is not about the games. Actually, there will be some three-dimensional games later, but today. But let us just watch some video about some. Well, might be first application of this geometry. Maybe not very important application in biology, but rather peculiar. So there is an uniformization theorem for Riemann surfaces. What is Riemann surface? This is a surface where where between any two close points there is a distance between them. This is more or less formal definition, and actually it can be covered by one of three geometries: by hyperbolic geometry, by Euclidean geometry, or by spherical geometry. So here you see torus covered by a plane. And what does it mean, covering? in which sense? Actually, you can cut your torus and form from the copies of it the whole plane in some coordinates, actually. Yeah. Yeah.
So, by real surface, you don't need the complex.
They always can be expressed as complex surfaces for compact ones. Yeah.
Okay, because here is the formula you go and then this is right?
Okay. So actually, if you have a surface of with at least two holes, actually it can be covered by hyperbolic plane. And let me show it to you. Yeah, locally. But wholly also, yes. Too. Angles should be orthogonal. So just some movements. Still doing. Yeah, my bad. Actually, I said to you that angles should be right, but they're not right. They're 120 degrees. Okay, here is an original octagon. Was it original tessellation? Okay. Yeah. Plain Quartic? So you are asking what is plain Quartic? Why it is Quartic, you mean? Where it is? Yeah, fourth degree equation. It means that you. Let me draw it to you. Oh, okay. Actually, it's some. Let me omit the detail. Why it's Quartic? Okay. Actually, it will lead us too far away. Yeah. So there is another video. We can watch it if you would like. Yeah. So probably. Actually, I was advised to do this in class, but I didn't buy any paper and glue. So actually, you can glue your own hyperbolic plane by just gluing 7 triangles around each point. So you can see the results. So since actually there is a tessellation of triangles with equal sides and equal angles, the angle is 180 degrees divided by 7. So it is some. So this paper model is motivated by this idea. If you glue up enough triangles, you will get something like this. This picture from Hyperbolic game. And my personal idea is to play checkers on hyperbolic plane. No one did code it for now. So, okay. Any questions so far? What? Into what? So in pentagons, right? So there are regular. No, these are not pentagons and quadrangles. Yeah. Actually, yeah. I don't know for now. Actually, this is a good question. I will think about it. Since the angles here are not 90 degrees. Okay. This will be a homework for me. Okay. So, other questions? Okay. So here is some mathematical part. Some problem part, some exercises part. So why part 3? Then this is part 3, yeah. Okay. Okay. Here you can see two tessellations, one for hyperbolic plane and one for Euclidean plane. So on the above you see regular pentagons with 90 degrees. Okay, maybe I should increase it. Okay. So and below you can see tiling with squares. So you run the process of filling filling the neighboring parts, how to say it, neighboring tiles of your tiling with some paint. And what will be painted? Which area? So for Euclidean geometry, you have quadratic wall of an area, yeah, 10 plus 1 squared. And how to compute actually the number of tiles for hyperbolic tiling? So there is a technique. You can do this sort of thing. So from the second step, you have the following property. So when you are moving around your painted domain, you add lots of pentagons, right? But how much? We can count the border polygons. So 10 one. So here are 10 ones here. Here are well, I mean this one, not the inside ones. Let me not count this by my hands. Yeah. So you're actually adding what? You're adding such so you so your polygons are coming in pairs, yeah. First one, second one, 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 yeah. And this here too, yeah. First one, second one, first one, second one, first one. Maybe. No, I will. Strange. But my formula works. Maybe I forgot some reasoning behind my formulas. Okay. So the polygons are actually so they are okay. No, I computed it wrong. Okay. So yeah. Sorry about this. This was my mistake. I was hurrying too much. Okay. Okay. So how to do this? Let us try to do this. Okay. Then what to do here? Actually, yeah, I forgot. So this will be my second homework for me. Yeah, I will explain it somewhat later. Okay, sorry. So actually, the conclusion was that the perimeter growth for this domain is exponential, and the area growth is also exponential, not the quadratic one, much faster. Okay, there was an exercise for you. Might be, I don't know, might be easier. Yeah, actually, can you do this? Well, let's do this the next time. Okay. So you remember the triangle area formula, and this is this one written, and here is an exercise for you. Compute an area for quadrangle. Yeah, so you just reminding you the formula for triangle. It will be useful. Yeah, but sometimes you just denote your angles as the corresponding vertices. But yes, that's actually I didn't find any picture for the formula and for the beautiful formula and for the and corresponding pitch, something like this.
Okay, no problem. For the next picture, we know the,
Yeah, we know these angles
are they
might be equal. Just arbitrary angles. The area formula for triangle is a hint. So we have a solution. Okay, let me switch to my paint. Okay. So the idea here is to divide this quadrangle by one diagonal. Here we have alpha and gamma, and here we have some x, y, z, and w, and we have that x plus y equals to beta, and z plus w equals to delta. And The area of left triangle is 180 minus alpha minus x minus w multiplied by t and divided by 180, and it is added with area of another triangle, which is 180 minus gamma minus y minus z multiplied by t divided by 180. Yeah? So what do we have here? We have t always divided by 180. Here we have 360 minus alpha minus gamma. Okay. What? Minus, sorry. Minus x minus y minus z minus w, which is just minus beta minus delta. Okay. So this is the answer. Where it is? Okay. So there is another phenomenon in this geometry, like hypercycle. What is this? Actually, since you don't have rectangles, but you have so you have something like quadrangle with symmetrical quadrangle with two right angles, two acute angles. The upper angles should be acute, since actually area should be non-negative, should be positive. And these two sides, left and right, are equal. So this is called a Sacheri quadrangle. And actually, I forgot to add some bio of mathematician Sacheri. Italian mathematician Sacheri. He was older than Gauss, Lobachevsky, and Bolyai. He also made some impact in the theory of hyperbolic geometry. And there is a notion of hypercycle, what it is. So for a line, you have a set of points which are distant from your line to some constant distance. Yeah. So this is denoted by radii. And so you draw a perpendicular of the length radii and just draw all the points P of this distance. And actually in Poincaré model, those equidistance will look like a circles not orthogonal to boundary. So this red circle is not orthogonal to boundary. And actually, there is an exercise for you. Why on this picture we do not see all the points that are distant from blue line on distance equals to LP? Why this picture is incorrect? Actually, I copied it from Wikipedia, but you can see here a hypercycle, but this is not an equidistant. So equidistant is when you have when you have points that are distant from a line on a constant distance. Let me tell you that maybe this is the formulation of my exercise is not correct, since we see these points, but they are not marked. Why? As a direction. Yeah, actually, there should be another hypercycle in another half plane. So this is one half plane, and then this is the other. Yeah. So there should be another hypercycle. Actually, I didn't think about it until this moment, but I think that they should be of equal angles between with the circle. I should check it. This is my third homework. Maybe we will do this in class somewhat later. Okay. Okay. Questions so far? Maybe repeat something. Okay. Probably no questions, and stop me if I'm not correct. Okay, we go to 3D geometry. So, this is a picture of Poincare model. Here planes are spheres orthogonal to boundary. In which sense orthogonal? It means that their tangent planes are orthogonal to tangent plane of a boundary sphere. Yeah. Here you see maybe some scary tessellation of by equal dodecahedrons. And what is the dodecahedron? It is 12-sided polygon with how much? 30 edges and 20 vertices, and in each vertex there how to say this in English? There are three neighboring faces, yeah, and 3 incoming edges. So this is how tessellation looks like from inside, and actually there is an exercise for you. Try to evaluate angles on the right picture. This one. Remember, all the dodecahedrons are equal on the right picture. And yeah, they are all regular. in the sense that they're symmetrical. So any edge can be moved to another edge by symmetry, any face can be moved to another face by symmetry, any vertex can be moved to another vertex by symmetry. Is this clear, actually? You can ask something. So. Maybe I should expand the picture. Okay. I can't. Maybe. So, any guesses? Actually, you can guess visually. What? Repeat. 30. 72. Why? I don't agree with you, but why?
Okay, well, you said that all dodecahedrons are equal.
Yeah.
And maybe from that.
Okay, so why 72?
360 divided by 5.
Why by 5, actually?
Fair point.
5 points. So, okay. Actually, sum of angles in each polygon is lesser than in Euclidean geometry. So you cannot use this formula from Euclidean geometry. But there is still... but you can still count from just 1 point.
Oh, then 120.
Repeat?
Maybe then 180.
No, didn't understand you.
Repeat?
Didn't understand you.
120.
120. Oh, okay. Okay. 120. No. At least why?
Oh, now from each point we have 3.
Okay. Okay. Number for each point. What number actually? The lines?
And the sides.
Okay. No, not quite sure about this logic, but okay. Actually, it's time to have another break, but do you want me to answer for this exercise right now or after the break? Maybe you want to think about it. Answer me something. What do you want? Maybe you want to continue, I don't know. Tell me.
I will think one.
What?
Let's continue.
So you want some solution, yeah? So, so before going to the break, I will tell you some solution. So you actually see, you actually said correctly that through each point there are 3 lines, yeah? For example, through this point, yeah? And this actually means that since 2 lines are forming a plane passing through each, yeah, so the angles in this plane are equal. So this is 360 divided by 4. This is 90 degrees. Okay?
I see.
Makes sense, yeah?
Yes, I see.
Okay. So this was just solvable exercise. Okay. Okay, let's have a break. Let's have a break, 5 minutes. Okay, answer me. Do we need longer breaks? No? Okay. Okay, dear Meatbags, let's continue. So those are ideal the guidance. I will call them in Russian way, and the ideal cubes. All the angles here are between lines are 0 degree. Okay. There are several videos for you. So this is some slicing of three-dimensional tessellation. Okay. There you can see chambers. Another one. Okay. Maybe, I don't know. So that's how you live in Hyperbolic house. Okay. Here is how object rescales in upper half space model. Yeah, so they are just moving balls, and they are expanding very fast when maybe okay, maybe not so clear. Well, you can see that they are becoming larger when they are moving farther from the bordering plane. Yeah.
This is your vision.
Yes.
Their area will be the same.
Yes, their volume will be the same. Their surface area will be the same. Yeah, this is some model for upper half space. So a picture for planes and spheres. Okay. And tessellation. So some very simple exercise, I guess, which polyeders can you spot here? Actually, let me tell you first that here are also some, how to say this, infinite faces polyeders. So you cannot, you might not spot them. You are allowed not to spot them, but what can you see? Yeah. This is just some combinatorial question, actually. I'm not wanting from you to compute any angles here. Maybe you can tell me how much types of polyeders here. What? Repeat. 5 types?
2.
2 types. Yeah, that's correct. So
3 and 7.
Repeat.
3 points and 7 points.
3 ones and 7 ones. Don't get. No, not polygons, but polyeders. Polyedron is 3D object.
Yeah, well, it's kind of hard to see this video.
I mean, one of them is tetrahedron. and
Yeah,
the second
tetrahedron.
is something quite complex.
Yeah, but we know some analog from Euclidean geometry for the second type. One type
What
is
about tetrahedron?
what?
Wasn't it tetrahedron?
No, not octahedron, since you can see a quadrangle and triangle. Yeah. So actually, you can see all sides for this polyhedra. We are talking about something like this polyhedra, something like this polyhedra. Yeah. So the tetrahedron is like this one, yeah, like this one. So, and we are talking about this polyhedra. So,
So it is, I don't think it is regular.
no, this is not regular.
So then it has quite complex name.
Okay. Well, okay. Okay. My initial intention was to call it a prism.
Ah, yeah, maybe.
Triangle prism. Yeah.
Isn't it? Ah,
Mm-hmm. Actually, I don't know how this tessellation was formed. I just copied it from one GitHub library, and so yellow planes are parallel, I think. Here, yes. Okay.
the second polyhedron has one edge. In the edge.
The central, which central?
One side that has 7 angles. And
This one. Actually, I'm not sure. Maybe. I see. Okay. We might consider. So this is a planar heptagon, right? Yeah, heptagon, and here is hard to compute. Actually, this seems that they're on the same plane, yeah? So this domain is probably polyhedra 2. Yeah, didn't think about it. Okay. Okay, let's continue. Some scary picture, probably. I looked at it for 10 minutes and spotted here icosahedras, cubes, and cuboctahedras. Okay, maybe if you want, I will explain where is there and what are icosahedron, cuboctahedron. Yeah. What? Cubes. Okay, I will try. I will try to at least remember where did I find it. Okay, cubes. So okay, yeah. Yeah. So you see a quadrangle here, yeah. So you see where it is. Sorry. There was a neighboring quadrangle actually. Yeah. Here is. Here is. No. Sorry. Maybe not. Maybe my bad. Maybe I was mistaken. Okay. Cube. Okay. Let's move on. So this how motions look like in the upper half space, like half plane, half space. Model. You can see that actually. So you can see that hypercycles are preserved by the motions. Yes, so you can see lots of shiny hypercycles here. And this is the version of this motion when you put second ideal point on infinity. Actually, maybe you want for me to explain why I call this infinity.
At least, how do you see the strange figures connecting to the point?
Those are two ideal points preserved by the motions.
And what is this worm?
Worm is a set of hypercycles which were just picked by the author of the picture.
And same for the points in the lower.
Yeah. Okay. Let's move on probably. So, actually might be not interesting. We saw this already. So, my favorite part. So, now we will work in hyperbolic geometry. Okay.
Hello and welcome to Lotto. In this video, we will take you on a one-of-a-kind adventure through various geometries. We study in a well-known and quite familiar
This is
geometry.
just Euclidean geometry
You might think that
right
you've
now.
seen this before because the world is made of cubes and it resembles Minecraft. However, this is not Minecraft. This is something more strange. And look at those arch-like structures. These are portals that will guide us to other geometries. And we will look for them in each world we will travel through. So without further ado, let's go through this Greek portal. You may need to adjust to the craziness of this unfamiliar world. We will do it slowly and explain the visual effects you will see. The first rule is do not be fooled by your eyes. The structures far away from you appear to be compressed vertically. They seem to be very, very narrow. But hey, look! As you come closer, this effect becomes weaker. The Euclidean geometry comes with perspective working differently than you would expect. Accept that your intuitions gained in the Euclidean world may be useless here. The second rule is pay attention to the shapes you see. Look, the world is no longer based on the cubes. We told you this is not mine. The faces we see here are pentagonal. Their edges may appear curved, but they are not. Again, this is only because the perspective works with you. The third rule is feel free to measure the angles. If you examine any of those pentagons, you will see that the edges are straight. Moreover, all angles of those pentagons are 90 degrees. And yes, this is a shape that is not possible in your Euclidean world. And this is not just a perspective trick. This work is really different. We are now in hybrid geometry. Even though the pentagons are weird, they are put on each other just like in the Euclidean geometry. Sidewalls and floors are plain old Euclidean squares. Okay, let's use another portal to understand where the weird pentagons come from. Welcome to three-dimensional hyperbolic geometry, the homeland of the weird pentagons.
So you actually see that this is branching everywhere, probably.
Now you see them everywhere, just like you saw squares everywhere in the starting Euclidean world. This is not hybrid geometry, so the perspective effects are more consistent. Now you see clearly that the edges are straight. Even though there are no stretching effects, the perspective is still not what you would expect. To your Euclidean brain, it feels more like us zooming in than moving forward. This is especially visible when we entered the quantum. We didn't want to scare you, so we slowed down. Now, let's cross the portal again.
Okay, so wait, in the continuation there is a spherical geometry. Okay, so how to say this? How to say 3D helmet in English? 3D glass? Yeah, this thing on his head.
Hi,
Yeah.
This is non-Euclidean virtual reality using brainwashing. So I'm in a vertical space full of cubes. I just want to well in my map is made up of cubes. But unlike the flat Euclidean world of my map, this is a negative curved space. So to illustrate this negative curvature, I'm going to walk around this pillar to my left. And to get our bearings, this cube that I'm starting in has this sphere down here, and there's the red light ahead of me, and there's the blue light on the right. So let's go here. So this world is curved, a little bit like how space is curved near a black hole. Light rays travel along strange curved paths and so on. And so there's going to be a mismatch between where I am in the real world and where I am in the virtual world. So I'm now back where I started in the real world.
So he didn't return on the same point in hyperbolic projection of his work, but he returned to the same point in his room. And this is just my idea was to show you that if you take four rounds of 90 of angle of right angles, you usually, well, you never returning to the same point again, actually, since there are no rectangles in this geometry.
You can see that where I started in the virtual world is one cube further in, there's a sphere and there's a red one there. So rather than walking around the size of a square to get back to where I started, I have to walk around the size of a right angle pattern. We make a simulation using a technique called brainwashing.
Okay, so here he is explaining the technology behind. This is just tracing his direction of movement. Okay, so more head spinning.
Here we are in the zero If you look straight up, straight down, everything looks about wrong. The cells above and below are just like the one for Let's move down and follow this easy long
Okay.
But what about the cells around you to the side? Well, notice the four cells are right here. Very similar. But after this, the lines are here to come out. Let's move forward to the right. See if we can get that. You can think of this as the cells moving the way I do it, and the way this model works.
So you can see writing it everywhere, probably. This is why it is just perfect for information storage, for applications.
And this all brings us a new down. First, each stage will be a fuel cell. At the center, you'll bring up 90 to the spider. From the center of this one, we make a non-linear radius to move to the right. From there, 92 is not creating the olive cell, but this core olive cell. Another 92 up, and we're coming into the center. And finally, our last one will bring us back to the olive cell. The path leads around that column will be regular along 6 and that's the kind of thing that we have when we take the curve.
And now, yeah. Actually, my head spined when I saw this video. This is a whole computer game set in three-dimensional hyperbolic world.
Hello fellow engineers and welcome to Hyperbolic. Now I've been following this for a while, but Dev has like a YouTube channel where he shows what he's been working on. Basically, this is a non-Euclidean style game. Now what is Euclidean, you might be asking? Well, it's basically like perception as you know it. So basically you can look at something and sort of see how big it is and work out how long it is, etc. This game, completely opposite of that, it basically makes you trip balls. If you're looking at this movie screen, you can sort of see it's a sphere that's rotating, but it's not quite rotating. I look over to the left side, it's like it's coming at you at a weird angle. But anyway, it's very hard to explain, so I think we're better off just starting the game. By the way, I have no idea what this game is about, only what I told you already. So, what's going on? Brain, primary stick, oh god. You don't disable that. Oh, I think the game's going to explain exactly what it is. Yeah, we're back at school. We're in geometry class. Geometry is such a fun and exciting subject. Yes, it is. The cornerstone of engineering. So, we're going over some of the basics. X squared for right angles. Correct. And 2 parallel lines stay the same distance apart. Correct. The circumference of a circle is pi times the answer here. But before we sleep, I think our character might be an architect. It's not very interested in this stuff. Alright, let's begin some homework. We are closing up a little bit. And oh dear, we're asleep. Oh god, obviously. What's going on? What's going on? Oh no, I don't like this. I don't like this. What just happened? Hello. Yes, we came from Virtual Learning Center. That's great. Me too. Welcome to Hyperbolic. Oh, that makes sense. It's a hidden mode. Only for extremely cool people. Yes, okay. So just what you pick up, so you might not get this level. So yes, it does look like we're on a planet, but it's just an illusion. It's really the opposite of our landscape. Right, so here we are. Yes, it very much looks like we are on the world, a little world. But as you walk around, oh god, it's so weird. It's so weird. What's going on? It's like it's far away, but it's not far away. Oh, I don't like this at all. Oh, help me. Anyway, he did actually give us a quest on Trippables, really, and Trippables. And he said, follow this path to the caravan site. So we're going to follow this path. Oh, look at that! I got the little pond thing, but it's actually a huge area. Oh no, this isn't right. This isn't right. We're just going to follow this path now. Where did this path go? Is that a trampoline? That's a trampoline. Right, let's go on the trampoline. Yeah, that's it. Oh, look, we're higher and higher. We can see the entire world. Oh my goodness, that is really. What? Oh man, the perception is so strange. I'm very confused at how someone made this. Because usually, like a 3D space is just like a 3D space. This is mental. It's like the computer did mushrooms before it rendered the level or something. Right, let's bounce off this. Oh, goodness. And by the way, this game is also VR compatible, so you could be tripping balls and probably vomiting. That's also that. So shall we go have a look? It's got a very.
So actually, locally, this geometry is really, very looking like Euclidean, but when you walk around it, you see some unusual phenomena.
Pretty door. Oh, there's a war in there. I can't open it yet. So it's like things like painted on, but when you get close, they're not painted at all, right? So we're still following this path, we've been following the beach. Oh, the beach! So it looks like a painting, but as you get close, it is actually 3D. Why, that's all the way around. Oh, it's so weird. Why is it so weird? Oh, look at this lighthouse. It is actually a lighthouse when you get close. Oh, what's it? You found a watch. You found a watch on the bottom. Okay. So yeah, lighthouse, as we walk away, it's gonna, oh, that's so weird. It's so weird. So I'm pretty sure this is where we started. This is the desk. This is the guy we spoke to. There's the sign. So if we get back there, here's the path. So we're opposite the beach. So there's the canvas. There's the farming thing, kind of tricking balls. So I think we're just going around in circles. No, let's keep going around. I feel like the longer we walk around here, the more different stuff there. Like, what? There's an entire city here, but we're still going around in circles. I've done like an entire loop. There's a city there. We're going around. Now there's like a car thing. Oh, then what's happening? You saw that place like 10 minutes ago. But this guy's still there. I think it's because the path is longer. And oh, I don't know. I really don't know what's going on. However, I think this is the caravan we're meant to get to, and I think there's going to be a map. Yes, he's given us a map. Alright, so we've just been told the request to find crystals. So we can open the map, and then things get a little bit clearer how it works. You can see in the center of the map, everything's sort of normal, so it's sort of easy to follow. But it looks like we're looking at it with like a fisheye lens, and that fisheye lens actually projects into the real world, and therefore it makes you trip balls. So we're going to go in this jump thing. So you go in here, I trip balls, ready. You go buckle down in here, dead ends, and go this way, dead end down there. There's two more dead ends, and then right should be the way out. There's actually another turn. Oh god, this thing goes forever. There is a way up there, that's good to know. Right, then we got this thing, which looks like we're going to trip balls in here. Let's go in, let's see what we got. Right, so where do we go? I guess we go read what the hell this is. Nothing to it. What's it? Just a little law. Oh, that now things have already gone wrong. There's things that were in you, go around the corner and no longer in you. Right, this guy's just asked if I can open up this YouTube channel. Sure, what's up, fans? Super I want you to come into the light of the rash new video. What should we say next? Oh, let's talk about a sponsor and make that fat cash. This video is sponsored by Funky Figures, connected to figures with the biggest media franchises. Right, just sending this video, please. This is not Bridget. What an action. Anyway, I'm very lost now. How do we get out of this place? Oh, I'm so confused. There's so many parts. There's so many parts. Basically, because this exists in like a normal space, I just can't get my head around how this works. Like, I just go left and left. Then left doesn't exist anymore. I'm so confused. Oh, thank goodness there is a map. So we can't find our way out in a way that our brain can recognize. Ooh, what is this? Is this one of the crystals? I think it's a crystal. Right, we're going to have to use this map to get back out. Firstly, it's open for us. Secondly, it actually get out of it. It all looks so simple when you're doing it in this game. So basically, I think as you walk along areas, like they change. So you can sort of see like that bend straight ahead of me with like 60 degrees, 70 degrees. But as you get close, it changes to 90 degrees. Oh, it's so confusing. Anyway, we finally found our way out, right? So now we're just looking out this little bit. I think there's a left there again. It's green! We're back on the never-ending path. Right, so let's see, can we go into the snowy area now? Yes, we've just been told there's a ceasefire. We can go in. Oh god, look at that fence. Look at that fence, that's not good. Right, so just if there's like a war going on, a cold war, because it's in the snow. This fence is freaking me out a bit, but also actually helping me, because it's telling me where straight lines go, assuming it is straight, that is. Ooh, let's follow these tracks. What's over here? Is that like, what's it, a catapult? I think it is a catapult. Do I get in here? Right, we're in. Someone fire me, someone press on it. Right, okay, here's a cube. I assume it's a cube. Into a cube. I'm scared like go around things in case it's not what I think it is. Okay, that was actually a cube. Thank you, game. I'm spinning out. Let's just keep following this fence. It's going to finish somewhere. And it does. It actually does. It doesn't end. Are they knitting needles? Yes, apparently they are. I've been going around the edge of this map for what seems like days, and I don't even understand. My smooth engineering brain cannot comprehend what's going on really. Oh, it's on YouTube again. Now, hold off me. I was flying back in the catapult. So, This is very hard to explain, but like going from that end of the fence to that end of the fence, next to the fence, it's like 20 seconds maybe. But doing it this end of the path, like by this catapult, which isn't too far from the fence, looking at it, it took like 5-10 minutes, right? Because we were challenged to a smooth fight, so push, eat some of that, push, oh look. Oh, wait, this curve, oh, ow, you hit me. Oh, sorry, this is really, really confusing. But I hit each of them 5 times. Bloody hell. You got that guy? Okay, the long ranges down the section. Right, we got you guys down. Eat some of that thing. Right, just yours, do that. Now, yes, we did it, right? So they give them a secret password, so like you can get catapulted over. Oh, triple balls just walking to the catapult rate, it's horrible. Yes, I have the password. The one handed down generation from generation. Right, we're in. Push, oh, God. Oh, no, this is not good. Oh, dear, oh, dear. Oh, the head. Right, it looks like there's a trebuchet when we do that. And as we know, trebuchet is the superior siege weapon. And what? Oh dear, what have we got ourselves into now? Right, she's given us some blueprints, we have to give them to Chester. I see Chester as an engineer, she doesn't know what to do with blueprints. She's only an architect. Let's give you that. Right, so we do that. Oh God, it's horrible. It's horrible. Don't like it. Now, I'm actually going to have to sort of call this as well. I'm going to throw up. This is disgusting. My brain just cannot have this. Oh, what's going on? I can only imagine what players would be on do to you. But yeah, give us now out. If you want to track yourselves, have a go. But you might need, go have a go, but you might need a strong stomach or a strong brain. I don't think my brain is the right type for this kid. It's horrible. You need a lot of nutrition. Anyway, guys, peace, love, and
Okay. Okay, are you good? After this, I don't know. My head is still spinning somehow. Yeah. So, how much is left for us? Yeah, actually, yeah, we have some time to watch several other videos. So short video. Okay. Okay, no commentaries. This is just some. What? Yeah. Hyperbolic Minecraft, yeah. So again, it's branching everywhere. Again, it's branching everywhere. What? What are you asking? Sorry. Okay. Okay. Yes. I forgot the right word about how I feel about this. How my body feel. Okay. So, this is a comparative comparison of two geometries. First one is, let's see. First one is about hyperbolic plane with vertical Euclidean line, just very vertical, you will see, and just standard three-dimensional hyperbolic space. The same game. So Not sure how gravitation works here. Probably it attracts the same ideal point, I don't know. Ah. Okay. Yeah. So, and here is some final game, probably, since we have 20 minutes, around 20 minutes. So this is Hyperbolic Tetris. Okay, bye. Why it stopped? Actually, people from Telegram say something.
Something?
Okay, so we are not, okay, so we are not disconnected. Hopefully. Why is the video stopped? I don't know. What? No, I don't know. Some lags are possible. I don't know. Sometimes. Okay. I see. So we have a low speed connection. Okay. No, I cannot increase it by my will. Will this help somehow? Not really. Okay, maybe you got the idea. Actually, you have a link for the video. Okay. So probably we won't see it today, but you can see what it looks like while I'm moving my mouse. Yeah. So okay. So if you want to understand how to live in hyperbolic world, you can just use these program products. Okay. Now, okay. How to imagine different models, actually. So we actually might need. So Klein model is pretty simple, but angles here are not very understandable. So it might be not familiar to work in Klein model. And about hemisphere and hyperbolic models. So next time we will discuss many dimensions. I prepared for you lots of slides about it. Maybe I can even show you something. Well, yeah, lots of videos. So actually there will be exercises, don't worry, you learn something. Okay, and actually there are lots of different models, since you always can change your coordinate system and do and walk around them. Okay. So, questions so far? If there are any. Maybe you want from me to explain something. Why did I show this to you? Well, actually, probably it is rather difficult to understand this geometry just from formulas. The formulas will be just as a third lesson, and I started from visual things, and this is about some phenomena from this geometry, and so at least you can imagine it. Actually, there is a whole. So actually, how to say this? Probably. Well, no. Let's discuss this later when we will talk about applications. Yeah. Imagination, yeah. Yeah, branching everywhere, yeah. Yes. Yeah. I hope you do not want it to apply it right today. Maybe you can wait for several days. Yeah. Yes.
I imagine the course where all the
Yeah. I understand. For actually, different types of perception for different people, different types of imagination. Actually, so for now we perceived it more or less intuitively, and so there are lots of. Okay, I didn't put it in my presentation for now. Here there in slides partly. I'm just preparing them. Yeah. So yeah. You will get this. You will get the formulas. You will get lots of things. Okay. Any other question? Commentary. So yeah, actually there are two final parts. Probably it will work. I didn't check it. Okay. So do you see a link? I can put it in chat. Yeah. So reflection part. Yeah. So how do I don't know. Okay. I don't know. Was write three things.
Some of us have a notification saying participant
What? So this doesn't work. Okay. So, okay. Sorry about this. No quiz for today, but I will send you a link for feedback. Please write something you want me to discuss later. Tomorrow or Thursday or Friday or something like this. Yeah. And actually I received just one course expectation from you. However, there are many of you, and probably you can add something. Yeah. Okay. So here I should write who was attending my lesson. So put your names on sheet. So, so who is A in? Arsenij. Which Arsenij? Are you in? Okay, thank you. So let me end the recording.